Okay. All right, let's try another problem. What if I give you this molecule, 3 hydrogens and a boron? Furthermore, let me specify that this is a neutral molecule, so it does not carry an overall charge. So let's start by having you draw a Lewis structure for BH3. So the way we would start, we would look at our periodic table. We've got essentially 3 hydrogen atoms, so 3 H dots, if you will. And then boron, where's boron here? We've got 1, 2, 3. Boron has 3 valence electrons associated with it. So we've just got to put the pieces together. Here's a boron with 3 electrons. And then hydrogens, each with 1 electron. And we know that a covalent bond requires 2 electrons to make. So if we put these pieces together, we might draw something like this. Or if we replace the bonding electron pairs with a line like so, we might draw something like that. So maybe that's what you came up with. BH3, also known as borane. And we will see borane as a reagent somewhat later on in the semester. Now the next question is the octet rule or the duet rule as appropriate satisfied for each atom in this structure? So see if you can answer that question. For the hydrogens, the answer is yes. Notice anytime hydrogen just makes 1 bond to something else, there are 2 electrons in that bond, and we count them for hydrogen to satisfy the duet rule. So duet rule, yes. Same for this one and same for that one. How about the octet rule for boron? We've got 2, 4, 6 electrons. So boron does not have a full octet of electrons here. Let's do a geometry problem. The last problem had to do with borane, BH3. And you saw that we could draw a Lewis structure that looked something like this. But this probably doesn't represent the real geometry of the molecule. So the question is, use the Vesper theory to predict the geometry of this molecule. Well, Vesper tells you to figure out how many things are attached to the central atom, which in this case is boron. So in this particular case, we have 3 things, namely the 3 hydrogens attached to B. And the way for those 3 things to be as far apart from each other as possible is a geometry of this type, where all 3 hydrogens lie in the same plane. So we could take that plane to be the plane of the blackboard. And the angles here are all 120 degrees. So write down, what is that type of geometry called? This is trigonal planar geometry. So using Vesper, we're able to predict that the geometry of borane, BH3, should be trigonal planar. Here's a question having to do with electronegativity. At least that's one possible way to look at it. Here is a Lewis structure of a molecule called formaldehyde. So according to this Lewis structure, carbon and oxygen are bonded by 2 bonds. So there are 4 electrons here that are shared between the carbon and the oxygen. So the question is, because carbon and oxygen are different, those 4 electrons are probably not shared to an exactly equal extent. How are those electrons polarized? Are they more toward the oxygen or are they more toward the carbon? And what are the implications for there being partial positive and partial negative character at the ends of this so-called carbonyl group? So how are those electrons polarized? Where's the partial positive? Where's the partial negative? To answer that question, we need to know something about electronegativity. So if we look at an electronegativity chart, oxygen is more electronegative than carbon. So these electrons should be polarized in the direction of oxygen. So perhaps you wrote a delta minus on oxygen and a delta plus on carbon, and the electronegativity difference between the carbon and the oxygen helps to explain the polarization of the carbonyl group.